Hello, and welcome to this presentation. The problem of creep-rupture life prediction for high-temperature alloys is very substantial for designing the power equipment, such as turbojet engines, turbines, chemical and nuclear reactors, steam boilers. Difficulties in the resolution of this problem are caused by a colossal complexity of microphysical mechanisms that form the long-term destruction processes in modern steels at creep. Numerous traditional methods for creep-rupture life prediction, which are based on the theory of thermo-activated processes, do not produce reliable enough results. They include the widely known Larson-Miller's time-temperature parametric method, suggested in 1952, and about 100 of similar time-temperature parameters. In the traditional approach, predicting equations contain a few special empirical coefficients. Their values depend on the class of the tested material as well as test mode. At the end of the 1970s, a group of researchers led by Goldhoff generalized and improved this experience by creating the minimum commitment method, recommended for use in the United States. However, to determine the coefficient for each specific material, a significant amount of preliminary experimental and analytical work is required. The significant part of empirical knowledge in the time-temperature parameter causes the uncertainty inherent to this methodology and limits the generality of the obtained findings. The extrapolation power, the ratio of the obtained time-to-rupture prediction to the maximum test time of the traditional methods, is usually no more than approximately 20. The duration of the material's testing phase, which requires the use of equipment and labor, is considerably long in relation to the projected results. We use an innovative nonlinear damage summation model for predicting creep-rupture life. This method has been developed by Dr. Vladimir Frayfeld, who is an expert in material science, specializing in long-term strength and reliability of high-temperature metallic materials, applied statistics, and design of experiments. He used a specifically developed version of the known phenomenological theory that interprets the gradual rupture caused by creep as a process of accumulation of diffused damage, micropores and microcracks in the material over time. While known models of damage accumulation lead to the hypothesis of linear damage summation at non-stationary loads, his new approach gives a more realistic and universal nonlinear damage summation principle. In the suggested new approach, any predetermined coefficients are absent. Therefore, it becomes possible to apply to the development of new high-temperature metallic materials of any chemical composition running at a wide range of temperature stress conditions. The new approach, along with its algorithmic realization, provides a good approximation to the real kinetics of damage. This allows us to achieve high certainty of the creep-rupture life predictions, along with the extrapolation power of approximately 2 orders of magnitude relative to the maximum test time. Our predictions may be obtained for both the mean probability of rupture and the corresponding small probability. Let's consider 2 examples of how the suggested method works. First, we'll review iron-based superalloy tested at the temperature 650 degrees Celsius. Having a few results of standard creep-rupture tests, with maximum test duration of about 1.5 months, we calculate the linear regression dependence of logarithm of time to rupture on logarithm of stress, along with other general regression statistics. Further, we perform the calculations in interactive user mode using our specially developed program and obtain a few calculated points. Using the points, we finally construct prediction regression lines of logarithm of time to rupture on logarithm of stress for the mean probability of creep rupture and the corresponding small probability. In our demonstration examples, we have the opportunity to compare the calculated creep rupture life with the results of long-term tests and show how close they are to each other. In this case, we obtained the prediction of creep rupture life of approximately 13 years. This prediction exceeds the maximum test time by approximately 120 times. Now, we will review a case for normalized and tempered chrome molybdenum steel tested at temperature 500 degrees Celsius. In this case, we obtained the prediction of creep-rupture life of approximately 31 years, while the maximum test time was only about 2 months. The prediction exceeds the maximum test time by remarkable 170 times. Here are the key benefits of the suggested method. The method provides reliable creep-rupture life predictions that exceed the maximum test time by approximately 2 orders of magnitude. It surpasses the known methods of the certainty of creep-rupture life determinations. The method will significantly expedite the usually long, laborious, and expensive process of determining the creep-rupture life of high-temperature metallic materials used in hot zones of power equipment. By reducing testing time, a reduction in cost of machine time and labor is expected. It is possible to apply the method to develop new high-temperature metallic materials with no analogs. An objective evaluation of this new method is possible based entirely on the results of short-term standard tests of creep-rupture life. At least 3 value pairs of stress time to rupture are required for input. Neither the class of material under test, nor its chemical composition, nor test temperature are required for calculation. Control data must be available for evaluation purposes upon produced results. By providing highly reliable, long-term predictions of creep-rupture life for high-temperature metallic materials, the suggested method will facilitate the rise of reliability, longevity, and safety of power equipment. Please visit us at crlsolutionsconsulting.com for more information.